Sometimes our circuits can grow in a very sophisticated form and we would like to determine the current or resistance or the voltage in a particular circuit element. And oftentimes, such circuits cannot be simplified by calculating the series or parallel equivalent resistance because paths have different EMF sources. Before we continue, let's define a few terms. So first, a junction, also known as a node or a branch, is a point on a circuit where three or more conductors meet. So in this figure, points C and points D are junctions. However, points B, A, E, and F are not junctions. Next, a loop refers to any closed conducting path. So in this circuit, there are three possible closed loops. I can draw a loop from point A to point B to point D, F, E, C, and back to A. That's one closed loop. I can also draw a loop from point A, B, D, and C. So that's another loop. I can also draw a loop from point C, D, F, and E. So that's also an example of loop. Kirchhoff's rules are easy to use because it only consists of two rules. The first rule, called the junction rule, states that the algebraic sum of currents into any junction is equal to 0. So for example, at junction C, if we have a current I sub 1 going to junction C, then it can be broken down into these two paths. I can rename the current going to this path as I sub 2 and the current going to this path as I sub 3. Apparently, this rule is based on the conservation of charge. So based on this diagram, I sub 1 is equal to I sub 2 as I sub 3. Or in other words, I sub 1 can be broken down into I sub 2 and I sub 3. And if I try to write this expression in terms of summation I equals to 0, then I'll just transfer everything on one side. And their sum must be equal to 0. The second rule, called the loop rule, states that the algebraic sum of the potential rise and potential drops in any loop is equal to 0. This loop rule is a consequence of conservation of energy. So first of all, let's try to observe some sign conventions. So if you have a battery or an EMF source, so this is the positive terminal and the negative terminal. When your loop enters the EMF source from negative terminal and then comes out from the positive terminal, you acquire or gain a positive potential difference or potential rise. Otherwise, if you have a battery wherein this is the positive terminal and the negative terminal and your loop enters the EMF source from positive terminal and comes out of the negative terminal, then you have a potential drop. So apparently, this rule is based on the conservation of energy. Let's also observe the sign conventions for the potential rise and potential drops when it comes to resistors. So when you have a resistor, and we assume that the current flows this way, though a resistor doesn't have polarity, we can assume that this is the positive side of the resistor and this is the negative side of the resistor because of the flow of current, and our loop is in the same direction as the current. Then we have a potential drop. Otherwise, if we have a resistor and the current flows this way, so we can assume that the resistor has a positive terminal on this side and a negative terminal on this side because of the flow of current. And our loop is anti-parallel with respect to the current, then we have a potential rise. Please remember these sign conventions. We will use this in solving circuit problems using Kirchhoff's rules. Let's have some examples. So for example, I have a 9 volts battery and I'll try to charge a 1.5 battery using this 9 volts battery. But of course, to avoid overheating or excessive transfer of charge or transfer of enormous amount of charge, I'll put a resistor, an external resistor from 9 volts to 1.5 volts. Let's call this R sub 1. Of course, each battery has an internal resistance. So let's represent the internal resistance of 9 volts battery as R sub 2 and the internal resistance of 1.5 volts as R sub 3. So let me draw this in a clearer way. Again, this is R sub 1, then R sub 2, R sub 3. Let's just name this as EMF 2 and EMF 3. Let's assume that R sub 1 is equal to 5 ohms. R sub 2 is equal to 2 ohms. R sub 3 is equal to 1 ohm. EMF 2 is 9 volts. Our EMF 3 is equal to 1.5 volts. So in using Kirchhoff's rules, first let's guess the direction of current for each resistor. In problems like this, I usually look for the EMF source with the largest value. In this case, this is 9 volts. So I assume that it will dictate the direction of current. So since 9 volts is the largest between the two EMF source, then I will assume that it will dictate the direction of current. So in this case, it will push the current in this direction. So it will push the current in this direction. So the current on R sub 2 goes this way and the current on R sub 1 goes this way and the current on R sub 3 goes this way. Now, it doesn't matter if you assume the current flows in an opposite direction because after calculations, when your current has a negative sign, then that means you have chosen a wrong direction for current. So in other words, after calculations, when you have a negative current, you just have to reverse the direction for that particular component or resistor. Next, try to draw an imaginary loop. So I'll just draw an imaginary loop that looks like this. Similar to choosing the direction of current, you can also guess the direction of the loop. It doesn't really matter because at the end of the calculation, if you have negative signs in the current, then you have just chosen an initially wrong direction for current. So you just have to reverse it. So the direction of the loop doesn't really matter here. It will just produce different signs, but at the end of the calculations, you will also produce the same magnitude of voltage, current, and power output, and so on. So let's start the calculations. So apparently we cannot use junction rule here because there's no junction in the circuit. So let's use loop rule. Again, in the problem, we are asked to find the unknown value of the current and the power output of each battery. So using the loop rule, the loop will enter first the 9 volts battery. So it enters from negative terminal and comes out from the positive terminal. So I'll end up with a potential rise. Next, it will pass through R sub 2. My imaginary loop will pass through R sub 2 and it is along the direction of the current. So I'll have a potential drop. Next, my imaginary loop will pass through R sub 1 and it is along the direction of current, so I'll also have a potential drop. And finally, for R sub 3, my imaginary loop will pass through R sub 3 and it has the same direction as the current, so I'll also have a potential drop. My imaginary loop will then pass through this EMF and it will enter the positive terminal and comes out of the negative terminal, and based on our sign convention, this will be a potential drop also. In a sense, this EMF here is acquiring charge from the circuit, actually reduces the energy of the circuit, so it's going to be a drop equal to 0. So I'll just plug in the values. Remember that E sub 2 is 9 volts minus I times R sub 2 is 2 ohms minus I times R sub 1 is 5 ohms minus I times R sub 3 is 1 ohm minus E sub 3, which is 1.5 volts, equal to 0. So I'll have 8 ohms, negative 8 ohms I equals negative 7.5 volts, and I'll end up with I equals 0.94 amperes. Now for the power output of the E sub 2 battery, remember that our equation for power is P equals IV, and we have a value for current, and we also have a value for the potential difference of the E sub 2 battery. So plugging in the values, we have 8.46 watts. Now for the power of E sub 3 battery, we have P equals I E sub 3, which is equal to 0.94 amperes times, based on the loop rule, sign convention, this is negative 1.5 volts, and we have negative 1.41 watts. Again, this sign convention is based on the fact that our loop enters the positive terminal of our battery and comes out from the negative terminal. So the negative sign here means that the current is running from the positive terminal towards the negative terminal of the battery, and it means that we are recharging the battery. If this is positive, this means that the battery is the one responsible for driving the current into the entire circuit. But in our case, it is the E sub 2 battery that's doing the work. So let's have another example. This example comes from OpenStax University Physics Problem 37. Consider the circuits shown below. I've just redrawn the circuit for part A. And for part B, the polarity of this battery is just reversed with respect to point C and F. So this is point C and this is point F. So in the problem, what is the current through each resistor in part A? Meaning to say, in this circuit. And what is the current through each resistor in part B? In other words, the same circuit but with V sub 2 in this configuration. Next, what is the power dissipated or consumed by each circuit? So in this case, we just add all the potential drops from the resistors, and then what is the power supplied to each circuit? This time, we just need to add all the potential rises coming from the battery. In this case, we just need to add the contributions of power coming from the EMF sources. So let's first assign the direction of current flowing through each resistor. When I assume the direction of current, I look first for the EMF source that has the largest value. In this case, it is V sub 1. So I'll assume that its positive terminal will be the one dictating the direction of current. So it will push the current this way. Something like that. For R sub 1, I'll assume that the direction of current is this way. And when it reaches junction E, it will be divided into this current and this current. So I'll assume that direction of current at R sub 3 is this way, and the direction of current in R sub 2 is this way. I cannot just use a single variable for current because obviously they have different values. So I'll name the current at R sub 1 as I sub 1, and at R sub 3 as I sub 3, and at R sub 2 as I sub 2. Next, I'll draw an imaginary loop. So I can draw an imaginary loop like this. Again, I can also draw it in this manner, it doesn't matter because you will still obtain the same magnitude of values later. For now, I'll just follow the direction of the current. So this will be my loop 1. And I can also draw another loop this way, an imaginary loop. So I can apply loop rule later. And apparently, I can also draw a bigger loop that encompasses the entire circuit. So this can be my loop 3. Now I'll apply junction rule at point E. So obviously, as current 1 enters point E, it will be broken down into I sub 2 and I sub 3. Next, I'll apply loop rule for loop 1. So first, my loop passes through R sub 1 and it's going to be a potential drop because its direction is the same as that of the current. So we have negative 2000 ohms times I sub 1. Next, my loop 1 will pass through R sub 2 and it's also a potential drop. And finally, my imaginary loop will pass through V sub 1. It enters from negative terminal to positive terminal, and therefore, this must be positive. Next, I'll apply loop rule to loop 2. My imaginary loop will enter R sub 1, but notice that it's opposite in direction with respect to the current I sub 1. Therefore, by our sign convention, this would be positive 2000 ohms times I sub 1. Next, our loop will enter this battery or the EMF source, and it enters from positive terminal and comes out from the negative terminal. And by our sign convention, this must be negative. So in a way, we are recharging the battery. And finally, our imaginary loop will enter R sub 3. And again, it's in opposite direction with respect to the current. So this must be positive 1000 ohms times I sub 3 equals 0. Now, I can apply loop rule to loop 3, but notice that I have 3 unknowns, I sub 1, I sub 2, and I sub 3. So, in algebra, if you have 3 unknowns, in order for you to solve the value for the 3 unknowns, you must have a minimum of 3 equations. I already have 3 equations, so I don't need another one. So, I will not be using loop rule to loop 3 because it's not necessary. I can already solve this circuit just by using 3 equations. So first, I'm going to rewrite this in such a way all the terms with unknowns is on the left side and all the constants are on the right side of the equation. I'll rewrite all these equations. So for the first equation, I have I sub 1 and I'll transfer this to the other side, negative I sub 2, and the same for I sub 3, negative I sub 3 equals 0. For loop 1, I have negative 2000 ohms. I won't write the symbol ohms for easier notation. And negative 1000 I sub 2, then 0, because there's no I sub 3 here, equals 1.6 volts. For loop 2, we have 2000 ohms times I sub 1. We don't have I sub 2 in this equation, so this is 0. And 1000 ohms times I sub 3. And it is equal to 1.4 volts. I arrange it this way so I can rewrite it in matrix form. So I'll have 1, negative 1, negative 1, negative 2000, negative 1000, 0, 2000, 0, 1000. And this matrix is multiplied to a column vector I sub 1, I sub 2, I sub 3, and it is equal to this column vector of constants 0, 1.6, 1.4. So I'm doing this because I will be getting the solution of these equations using determinants. So you could actually solve this bunch of equation using brute force substitution or other means, but I'm going to show you the easiest way. So right now I was able to write the bunch of equations in the form of a sub 1, b sub 1, c sub 1, a sub 2, b sub 2, c sub 2, a sub 3, b sub 3, c sub 3. Equals constants. B sub 1. Now, when you have a matrix in this form, then you can actually calculate for x, y, z using determinants. And when you want to calculate for x, you just calculate for the determinant for the x components divided by the determinant for this entire matrix. And the same goes for y. Y equals d sub y divided by d, and z equals d sub z divided by d, or the determinant of this entire matrix. So first, let's calculate d, or the determinant of this matrix. So again, d is the determinant of this matrix. So I'll write down 1, negative 1. I made a video tutorial on how to calculate the determinant of a matrix using a scientific calculator. The link is in the description box below. Using calculator, the determinant of this matrix is equal to negative 5.0 times 10 raised to 6. Next, I'll calculate for d sub x. And d sub x is actually the determinant of this matrix, but I'm going to replace this column with this column. Okay. So I'll have a bunch of constants in the first column. 0, negative 1.6, 1.4, and I'll just copy this. So using the calculator, d sub x is equal to negative 3,000. Next, I'll calculate for d sub y. And d sub y is the determinant of this matrix, but we will replace this column with this column. So this is, I'll just copy this first column, which is 1, negative 2,000, 2,000. Then this one, 0, 1.6. I think this is one negative, sorry, 1.4. And then this one, negative 1, 0, 1,000. So using the calculator, I'll end up with d sub y equals negative 2,000. Finally, I'll calculate for d sub z. It is the determinant of 1, negative 2,000, 2,000, and then 1, negative 1, 1,000. And then I'll just copy this. So using the calculator, d sub z equals, so I sub 1 is equal to d sub x divided by d, which is equal to negative 3,000 divided by I sub 2 is equal to So for part A, I sub 1 equals the numerical value of this, which is equal to 6 times 10 negative 4 amperes. And similarly for I sub 2 and I sub 3, just calculate the numerical values of these expressions respectively. We have 4 times 10 to negative 4 ampere and 2 times 10 to the negative 4 ampere. Now for part B, let's return to the circuit. So for part B, we will be using this same circuit, but V sub 2 is in this direction with respect to point C and point F. So observing our loop rule will then pass through the negative terminal to the positive terminal. So in effect, its only difference is the change in the sign of this loop 2 equation. So this will become positive 1.4 volts. So in our matrix, original matrix, this will just become a negative sign. So let's rewrite the matrix here, but replacing positive 1.4 volts with negative 1.4 volts. So again, we have the same matrix. The determinant of this matrix using scientific calculator is equal to negative 5.0 times 10 raised to 6, and d sub x is the determinant of this same matrix, but again I'm going to replace the first column with these values. D sub x equals negative 200. Next, d sub y is the determinant of this matrix, but I'll replace this with this. D sub y equals negative 7,600. Finally, d sub c is the determinant of this matrix, but I'm going to replace this with these values. So I sub 1 equals 4 times 10 raised to negative 5 amperes or 0.04 milliampere. I sub 2 equals 1.52 milliampere. I sub 3 is equal to negative 1.48 milliampere. So the negative sign here means that the direction for I sub 3 is reversed. For part C, we just have to calculate for the dissipated power in the circuit. So for the power in circuit A, and this is equal to 0.92 milliwatt. For circuit B, this is equal to 4.5 milliwatt. For part D, we just need to calculate the power supplied by the EMF sources. So for circuit A, if we return to the circuit, the current that passes through V sub 1 is I sub 2, and the current that passes through V sub 2 is I sub 3. And this is equal to 0.92 milliwatt. And for circuit B, it's equal to 4.5 milliwatt. Kirchhoff's loop rule is based on conservation of energy. That's why the power dissipated and the power supplied are equal. And the same goes for circuit B. Notice that the power dissipated is equal to the power supplied. Don't forget to like this video, subscribe to my YouTube channel, and hit the notification bell button for awesome updates. Thank you for watching!